Recording has started.
Alright, today we're going to talk about the lecture 19, and then we will go over the solutions of the second midterm. So let's first talk about this flash memory. So this is one of the memories that we discussed earlier in the memory hierarchy. This is for the SSD, solid state drive. But the building block is a flash memory. And this is a reference chapter and the recorded materials from last spring and Professor Asif Khan. So flash memory, and you have used those flash memory based SSD or USB or SD card in your daily life. So this is a key enabler of the digital media, like the storage for your photos, your video, and so on. So this is what we use every day. The flash memory is built on the floating gate transistor, and today we are going to discuss more details about the floating gate transistor. So this is the data storage, and as we discussed earlier, flash is a non-volatile memory. That means you can store the data even after the power is off. So that's why you can maintain the data for many years. Alright, so then the building block for the flash memory or the SSD is based on this so-called floating gate transistor. So the flash memory cell is actually like a transistor. So here the difference is that the floating gate transistor has additional floating gates in the gate stack compared to the MOSFET, regular MOSFET. So here we have the regular MOSFET. Then you have one oxide. This is the gate oxide, and only one gate. But the floating gate actually has two gates. So between those two gates, those are still oxide. So here you see this light gray region. So those two regions are actually oxide. So still you have the TOX, like the oxide thickness. So you have two oxide here instead of one oxide in the regular MOSFET. Therefore, you have two gates. One is this floating gate, one is the control gate. So the control gate is similar like the regular gate, where you can apply the voltage. So this is like the terminal to the external circuitry. But the floating gate is floating, so you don't have the direct access to the floating gate. So then this is somewhere in the middle, like floating. You don't have the direct access. As floating gate is separated from the control gate through this oxide, or this is also separated from the channel through another oxide. So this is somewhere in the middle. And the floating gate is typically made of the doped silicon, because the doped silicon is conductive. So you can use that as the gate material. It's like metal. So this is a key difference between the conventional MOSFETs and the floating gate transistor. Then the principle of the floating gate transistor, or the principle for the flash memory, is based on the charge, and in this case, electrons stored in the floating gates. So here we have two states, and if the floating gate does not have electrons stored, we call it erased state, and this is representing digital 1. And then if we have the electrons stored in the floating gate, then this is a program state, or we call digital 0 state. So basically here we rely on the electrons that are stored in the floating gates to represent different memory states. Either you have electron or you don't have electron. If you have electron, in this case we call programmed state or 0 state. If you don't have electron, then it's erased state or one state. So here the operation principle is based on the transistor's IDVG curve. So here this is the ID, a drain current, drain to source. So still you measure the current from the drain. And then here the voltage we show is a control gate, VCG. Is the voltage you apply to the control gates because you can only access to the control gates instead of the floating gates. So you apply voltage to the control gates. And then we show this IDVG curve. So here the key difference of those two memory states is the threshold voltage. So here you see this is like the threshold voltage. So the threshold voltage is different in those two states. And you can see here this is the one-to-one correspondence between the erased states. So we have this green curve for the erased states, IDVG or VCG. Then this is a blue curve for the program states. Then my question is, why would the threshold voltage shift if you have electrons stored in the floating gates? Compared to the erased state, you don't have electron. Then the program state, you have electrons there. And you see here the threshold voltage increase, right, when you have electron. When you have electron, then the threshold voltage increase. So why is that? So you can think that here the electrons, right, you have electrons in the floating gate. Then you apply, this is a NMOS. So floating gate transistor is always NMOS. That means the channel is p-type, source and drain is n-type. So here to turn on the NMOS transistor, to create the inversion in the channel, you need to apply positive voltage larger than threshold. But if you have negative electrons in the floating gate, you need to apply additional positive voltage. Why? Because some of the positive voltage, when you apply positive voltage here, you are going to induce positive charge on the control gate. But if you have electrons in the floating gate, some of those positive charge will be screened by those negative charges. So you need more positive charge on the control gates to induce the electrons in the channel. Compared to the erased states, then you don't have the electrons in the floating gate. So you apply some gate voltage, then you can induce the electrons in the channel. This is how you turn on the transistor. But now if you have more electrons in the floating gate, then you need more positive charge on the control gate. That means higher voltage on the control gates. That means the threshold voltage will increase. So here you see the threshold voltage is a key indicator of those two states. And then this is the difference between those two states. And later how you sense the difference, how you read out the memory states. So what you can do is to bias the gate voltage, the control gate voltage to this read voltage level. So if you apply voltage somewhere in the middle between those two threshold voltage, then you can see that if the floating gate is in the erased state, you have large readout current. If you are in the program state, then this is below the threshold, then the current is small. So later you use the current difference to detect which data you store in this floating gate transistor. So basically you need to apply voltage, read voltage between those two thresholds, and then one will read out the current, and that is erased state for the one, and then for the program state, then the current is very small, this is sub-threshold, then you rely on this current difference. So here you will see the current difference, delta I. So any questions about the principle of this floating gate transistor? Okay, then let's look at how we program or write the data into the floating gate transistor. So here, as we mentioned, for the program, we need to inject electrons into the floating gate. And the way we do this is to apply large gate voltage. So this is really large, like 12 volts, sometimes even more than 20 volts. So we have a large gate voltage, and then the electrons will inject from the substrate to the floating gate. So this one is the floating gate across this oxide. So normally this will not happen in the regular transistor because oxide, as we know, is like an insulator. So current should not flow across the oxide. This is the nominal case. But when the voltage is very large, like 12 volts, then this is like the Venn diagram between the channel, and this is this oxide, and this is the floating gate. So it's like this channel, oxide, floating gate. And we know that we will apply large voltage on the top. That means we are going to lower down the potential of this floating gates by this large voltage. So if you draw the Venn diagram, and the floating gate, as we discussed earlier, is typically still the doped polycrystalline silicon. So it's still silicon. So you have two sides silicon and then separated by the oxide, silicon dioxide in this case. So because this band is so bent by this very large voltage, so the electrons in the substrate will see a very triangular barrier. So previously, let's say if we don't apply voltage, the band is like this, right? So both sides like silicon. And then the electrons will see this barrier. And normally, the electrons cannot cross over. But when we apply very large voltage to bend the band like this, then the electrons will see relatively thin barrier, very thin. This is like 1 or 2 nanometer. So here, so-called the FN tunneling will happen. This is a quantum mechanical effect. So electrons normally cannot move across the oxide or this barrier. But when this barrier is very thin, like 1 or 2 nanometer, due to the quantum mechanics, the electrons will have certain probability to tunnel through. So this is a tunneling effect. And we're not going to discuss the details of that. This is pure quantum mechanical effects. So basically, quantum mechanics tells you that there's a probability to find the electrons on both sides of this barrier. And the electrons like a wave. So if you look at the quantum mechanics, basically it tells you that any particle is also like a wave. So there is a duality between particle and wave. So if you think the electron is a wave, then the wavelength of electron actually is like a 10 or 13 nanometer. So the wavelength of electron is larger than this barrier thickness. Then you can have some probability to find the electron in the other side. So this is like a tunneling effect, purely quantum mechanical effects. And this will only happen when you apply very large voltage. Normally, then the electrons should not turn through. But in this case, we intentionally apply very large voltage. So that's why in the flash memory circuits, then you need to provide very large voltage on chip. So anyway, so this is how we inject electrons from the substrate to the floating gate. And this is like you write data 0 to the memory cell. And then we can also write data 1. So this means we're going to erase those electrons from the floating gate to the substrate. So initially you have the electrons here, and now you want to get them out. So similarly, you should apply very large voltage, but in this case, we're going to reverse the direction of this electron flow. So we apply 12 volts to the substrate. Previously, we applied 12 volts to the gate, so the electron turns from the substrate to the floating gate. But now we change the direction, so large voltage on the substrate, so electron will similarly turn through the oxide, and then you get rid of those electrons. So this like you erase the data, and then this is like write data 1. So any questions? Alright, then this is just a one floating gate transistor, one cell. But memory array, we need to organize the memories cells into an array. And this is one way to make the array. This is called the NAND flash, NAND array. And in the NAND array, we are going to have those floating gate transistors. So here the symbol is a little bit different. So we have double lines in the gate to indicate this is like a floating gate. Instead of the regular transistor, you only have one line here. So you have double lines. This is like a floating gate. So you have those floating gate transistor in series, like a string. So here typically one NAND string will have like 32 to 64 floating gate transistor in series. And this is like number of word lengths in this array. And it's like 32 to 64. And this is like the vertical side. And then horizontally, we have many bit lengths. So bit length can be up to like 2K to 16K bytes. And that means you need to multiply by 8. This 1 byte is 8 bits. So that means it's like 16K to like 100K bit lengths along this direction. So it's very rectangle, one block. So here this is how you organize the flash into the NAND array. And the read and program operations are performed per page. So here one page means one word line, so one row of the array. And the read and program operations are performed per page. That means you can read out the whole page at one time, or you program the whole page. Program means you write data 0 to this whole page. But the erase is performed per block. It's not random access. So this is a key difference. So you cannot individually change the data. So that means if you think about the whole array, you erase all of them together. You cannot individually erase. That means once you want to write data 1, you have to write the whole block like this. So the whole block will be read to 1 at the same time. This is because all those transistors share the same substrate. If you see here, this is how we erase. So we apply 12 volts to the substrate. But if you can think that there are many transistors in this block. All of those transistors share this substrate, shared silicon substrate. Once we apply 12 volts, we apply 12 volts to all the floating gates in this block. Therefore, all of them will be written to 1 simultaneously. Therefore, this array will be erased to all ones. You cannot individually write 1. That means this is not random access. So the whole array will be written to 1, and later what you can do is to write 0 page by page. That means row by row. So you can write first row, some of the cells, depending on your data pattern. So you can change some of them to be 0. Then that is the real data you want to store, for example, here in the first row. So this is how we operate on the NAND flash. So the NAND flash is kind of slow compared to the DRAM or the SRAM because the time to program the erase typically can take up to hundreds microseconds. So this is much slower than DRAM's tens of nanoseconds or SRAM like 1 or 2 nanoseconds. So this is like thousands times slower, or tens of thousands times slower. So any questions? So we'll stop this part.